Hello, good morning. We got a lot of background on drivers for running new data centers, and I want to talk about a particular technology that's being standardized to support that. So let's see if I can figure out which button to press. That's this button. Okay, here we go. Okay, so Omar did a great job talking about RDMA as a driver. I mean, it's really about the applications. There's a growing number of low latency type of applications that we're trying to run in data centers, particular distributed storage, as we talked about, artificial intelligence. And trying to do this at cloud scale is where we start running into trouble. Omar talked a great deal about a lot of the knobs that you have to set and configure to make this work. And so we're really trying to figure out how can we do this in a much easier way. There's a number of papers here that have been referenced about RDMA, running it at scale, things that have happened recently to try to make it work in bigger networks. These are great examples that we can look at. But in the end of the day, what we're really trying to do is really trying to take that high performance computing and RDMA type of network that was traditionally very private, very customized off to the side, and make that mainstream, make that a workload that's in a hyperscale type of data center. So what do we have to do that? And because that's the goal, right? Getting things bigger, cheaper, faster. And so we got to eliminate a lot of that complexity of the configuration and things that we just heard about, and we got to try to figure out what it's needed to really make it scale at that level. So those are kind of the key drivers. So we kind of saw a network already. There was a great talk yesterday about CLOS networks. That's really kind of the state of the art of data center networks. So they're kind of layer 3 networks with layer 2 links configured in a kind of a CLOS style configuration. And Omar showed this slide as well, which is sort of the way congestion is kind of handled today in those networks, which is relying on the support of the network to identify when there's congestion, marking those packets so that as they travel across the network from, say, left to right here, the destination can determine that these packets were experiencing congestion. So it can signal back to the source through the acknowledgement process that there's congestion on this path. So why don't you slow down your rate of injection, and then hopefully that congestion will subside. So that's kind of the key thing that happens. Now, also, Omar talked about RDMA, which was evolved on top of InfiniBand, which was fundamentally a lossless fabric. So a lot of the protocol was built in order to assume, hey, I'm not going to drop packets at layer 2, so we can simplify things and we can offload everything onto the NIC. So if we're trying to emulate that on Ethernet, how do we create a lossless Ethernet environment? And so, ultimately, you have to rely on this priority-based flow control in order to not drop a packet. This is where things get really complicated and difficult to configure, as we sort of described. Today, traffic classes are sort of identified too, using layer 3 DSCP code points, for example. Perhaps maybe not even using VLAN headers. But so this is kind of the state of the art today that exists in a lossless network. This is getting increasingly difficult to support going forward. So if you, as we talk about, we want to scale the network, so we're going to have more hops, which means there's more data in flight. But at the same time, we're speeding up the links. We're going to 100 gig, and now there's 400 gig switch ports available. So there's a ton of data in flight, but the amount of memory per packet, per port, per gigabit is actually going down. So this is looking at some Broadcom silicon and looking at how much buffer do we actually have available as this performance goes up. And it's physics. It's really difficult to build silicon with that much memory and speeds as they go up. So we're really putting pressure on the switch buffering. And another important thing is we want low latency, as we talked about. So having small buffers is good, but as we get bigger and we have faster links, we're going to have more data in flight, so it's more difficult to absorb the bursts, if you will. So we run into the scenario of perhaps using priority-based flow control more frequently than we want to, and the side effects associated with that. So 802.1, which is where we do the standards for Ethernet switching, has a couple tools in their tool bag, and we talked already about priority-based flow control, and most operators that I'm aware of don't like it, don't use it. If you use it, perhaps you use it at the edges of the network only, or you're using it in a very small, isolated, high-performance cluster. And part of the problem is you have to tune all of the thresholds and things exactly right, and it differs from one vendor to another, perhaps even one switch model to another switch model. The parameters are different, so calculating the amount of buffer you need to assure that you'll never drop a packet while that pause frame is transitioning the link can be very complicated. But it also has some negative side effects, as we talked about. The head-of-line blocking, which is when I pause a traffic class, that means everything in that traffic class upstream will stop. Even if a flow is going somewhere else, away from the congestion, that creates a head-of-line blocking scenario. And then as we wait, as we back up in one switch, we'll push back to the next switch and push back to the next switch, and ultimately potentially bring the network performance down to the slowest link or the congested path on the network. So congestion spreading becomes a huge problem. And the sort of X-on, X-off approach that priority-based flow control has creates some oscillations in the network, and you end up with what we call buffer bloat, a lot of jitter, and a lot of just sort of strange behavior. In some cases, even deadlocks. So it's possible to have priority flow control in a circle and effectively locking up the network. So it's not a favorite tool people use. However, for a lossless network, it is sort of your last gasp. You must use it. You don't have another option right now. 802 also invented congestion notification, as Omar briefly mentioned. That was really built in order to support what we would call a large layer 2 network running protocols such as RDMA or even fiber channel over Ethernet that didn't have their own really congestion control layer or transport layer. So the layer 2 network itself built a congestion management scheme that would, again, identify congestion and signal all the way across the layer 2 fabric to the source, and have that source would then adjust his rate. Again, we don't build as many large layer 2 networks anymore in order to scale, so this technology didn't get adopted too much. Things like fiber channel over Ethernet and the first version of Rocky didn't have wide deployment. And also the NIC vendors, I would argue, really didn't like this scheme because they already are managing the rate injection by the higher layer transport protocol, so the end-to-end congestion control. And now they have a layer 2 message that they're also getting, and they have to reconcile rate control coming from the fabric as well. So it was kind of a difficult implementation on the NIC as well. And so it didn't really have very wide adoption. So the project that we're working on now, called Congestion Isolation, is really an attempt to provide layer 2 support without the complexity of these other protocols, and to allow scale as well. So this is called Congestion Isolation, and it was a project that has been going on for a while, but recently adopted, and drafts are now kind of currently being written. And so we're in sort of the balloting process of that. The motivation for this is one of the technologies described in the NINDICA paper that Roger mentioned as well. So if you get a chance to read that NINDICA paper, you can see some of how this fits in with some other technologies such as load balancing and also push and pull kind of different scheduling transports as well. So some other interesting topics there. So let me explain a little bit more about congestion isolation, how it actually works. Okay, so first of all, we talked about the state of the art. Here's how things look today. We're in support of end-to-end congestion control. So we're assuming that the higher layers have something that is going to slow them down, right? TCP, or if it's a quick or something along these lines, or a UDP-based protocol, it has congestion management itself. So end-to-end exists. And today, again, if we wanted to be completely lossless, we would use priority-based flow control to push upstream to stop so that we don't drop packets. So that's kind of how things work today. It has those side effects of creating head-of-line blocking. So with congestion isolation, in summary, what we're really doing is we're defining two traffic classes. You have a single traffic class where everything is running, and then we have a separate traffic class that we're going to isolate flows that are creating congestion. There was also a talk the other day about the ISP in a box, and I think he talked about FQ-Coddle as a scheme for queuing that really did a great job of maintaining predictable latency for wide area communications. There's some similarities here. We don't have per flow queues. What we're doing is we're aggregating, but we are using a separate queue for flows that are causing congestion, and we are re-queuing them. So what happens here is when that congestion is building and the switch is beginning to mark packets with ECN so that it'll go back to the source, the switch will also at that time begin to queue subsequent packets for those flows into a different traffic class. So it kind of moves them out of the way. And then we'll generate a message, we'll signal to our upstream switch, and in that signaling we have enough information that you can identify the same flow. So the upstream switch will now do the same thing. It'll isolate the flow, move it to a different traffic class, and as a consequence we've moved it out of the way, so we've eliminated the head-of-line blocking. So now in this example, the blue flow here is able to go through the congested path without experiencing any delay. And what we're doing fundamentally is moving that congested flow out of the way. We're sort of leveraging some of the switch buffering to delay dropping the packets and allowing the end-to-end congestion time to take effect. So meanwhile, the acts are going back, the source is slowing down, and then eventually we're assuming the congestion will subside. So we're sort of temporarily buffering congested flows, if you will. It's kind of at 50,000 foot level, that's kind of how it works. So the goals were not to replace end-to-end congestion control, but to work with it, to allow that to work more effectively. And to support, again, larger scale, faster data centers with super low latency to support like NVMe over Fabric, storage protocols that need sub-microsecond type latencies. Support those low latencies while maintaining high throughput. Don't make that trade-off. And again, support a lossless environment for those protocols today, or just a low loss environment. So it's not required that you use priority-based flow control, but if you want to, you'll have a lossless environment, and we'll use it less frequently. And we'll show you some simulation results of that. Another goal was to not be protocol specific here. We want to be agnostic, whether it's TCP or UDP, we don't care. So it is flow aware. And we want to try to do this without requiring you throwing more memory in the switch. So we're trying to be effectively intelligent queuing, not just more queuing. So that adds delay and cost. And again, it's very difficult as we build higher speed switches. So we're trying to reduce the buffer growth that's required, reduce the relying on PFC for the lossless environment, and again, eliminate that head-of-line blocking. And so there's a diagram Roger showed. I'll go through it in a little bit more detail here. So imagine you've got your cloth fabric, and we're just going to take one slice of that, looking at an upstream and a downstream switch. Obviously, traffic's coming from all different kinds of directions here. But in this scenario, the first step is that the downstream switch is starting to experience congestion on the egress port. And when it's doing that, it's going to mark ECN bits in the header. So it knows which flow now is potentially causing congestion. Now it's going to do that using a sampling algorithm, or depends on the switch architecture, how it's built. So there's some chance of being incorrect here. But this is a best practice that's been being used, right? So something along the lines like random early detection, but maybe a little more intelligence. So we identify that flow, we're marking the headers, and now we're going to queue packets into a different traffic class. And we're going to schedule those traffic classes differently. So clearly there's an opportunity here to have an out of order packet situation. So we have packets already in a queue for a flow, and now they're going to go into a different queue. So we need to kind of deal with that complexity, but that's an internal switch architecture issue, hopefully. We're not going to see these on the wire. Okay, so we've identified the flow. We've begin to queue the packets into a congested queue, and then we signal to our neighbor that we're doing this, and we give them enough information to identify the very same flow. So now the upstream neighbor will do the same thing. It'll begin to queue those packets in a different queue and eliminates the head-of-line blocking, getting it out of the way. Now, if we do begin to fill up and we want a lossless environment, the goal is now I'm only putting the pause on the congested class. So I'm only penalizing the guys that are really causing the problem here. I'm not penalizing everybody. So if we're using lossless, hopefully it's only occurring in the congested class. So that's effectively how it works. Devil's in the details, obviously. And some of the key processes, again, are detecting which flows cause congestion. And again, most routers and switches already have a means for doing that. They're setting the ECN bits, so they have some mechanism they're already using. In the standard, we can specify existing methods, so we're not going to define a new method here. So that's really up to vendor innovation. Once we've defined that, we're going to need to create a flow entry in the switch that recognizes subsequent packets of a congested flow. So there is a new flow table, if you will, that would be required. The good news is you can build this in a way that you're only holding the congested flows in that flow table. You don't have to know about every flow in the network. You only need to know about the ones that are currently causing you a problem. So we can limit that resource. We don't have to make a huge flow table. Again, the critical process of signaling to your neighbor, that could be optional. We've talked about not doing this and just doing the isolation locally and measuring the impact, but you'll see it does make a difference to tell your neighbor what's going on. So signaling is the key process and how that works in. And then managing the out of order issue. So we're going to schedule those two queues using the enhanced transmission scheduling or sort of some bandwidth allocation, weighted fair queuing. And we want to make sure we don't deliver packets out of order. So there's a bit of an implementation detail that can be a little complex in that. If you want to just use strict priority, that would work. But however, you have the potential for starvation with that scenario. So that's another issue. There's some tricky things with interacting with priority-based flow control as well, because as I mentioned, the goal would be, if I'm going to use it, I only want to use it on the congested class. However, there may be packets in flight on both queues, and so there's some complexity related to how we might interact with that and make sure we're pausing the correct traffic class. So again, and then once a flow has been determined to be causing congestion, at some point we expect it to slow down because we have end-to-end congestion control. So we need to know now, when is this flow no longer a problem? When can I return it to its status of a non-congested state, if you will? And how do I do that without creating another out-of-ordering situation? So these are the critical processes that the standard itself is identifying and documenting. Clearly, for interoperability, anytime you signal messages on the wire, we have to have a protocol spec. So that's another aspect of it. But a lot of the details will be up to the switch silicon vendors on how they choose to implement these various processes. We did some simulations. There's a lot of data available on these reference slide decks that show whether this is effective or not. We kind of set up a CLOS network using OmniNet ++, and scaling it up to about, say, 1,000 servers. So it's not a huge simulation, but enough to show the difference here and the ability to scale. The traffic models we used were a mix of the incast that you see with like AI applications and storage applications, also with the many-to-many. So we kind of had this rough mix of different traffic patterns in our simulation data. And what we measured both the lossless and the lossy scenario, And in the lossless scenario, we were basically measuring flow completion time. So we want to see an improvement in overall flow completion time across the network. And in general, we saw, say like a 38, almost a 40% improvement, which was significant enough to warrant doing this project. If it was only a small gain, you'd say, well, let's just throw bandwidth at the problem. But we're seeing a 40% improvement across all flows. Obviously, the bigger the flows, the more of a gain that we see in this lossless scenario, almost up to 60% improvement in flow completion time. There's some proprietary technologies that are out there that do some things where they separate the mice and elephant flows today. So you may have a switch that recognizes all packets as being a mouse flow, if you will, initially, and then if the flow persists for a long time, it's designated an elephant flow, and then they may use different traffic classes for that. Cisco has a feature that does this. We also looked at, okay, well, what if we have that capability, mice-elephant separation, plus a congested flow? What kind of gains do we get? So you can see just separating mice and elephants alone was pretty useful, but adding congestion isolation on top of that still gave us a 25% gain on flow completion times again. So it was a kind of very useful feature even with other enhancements that people are doing. In the loss C scenario, so we're not doing priority-based flow control here, so we can have packet drops. The goal here was to see, well, how do we improve packet loss ratios in general? And then we also compared doing this with signaling your neighbor and without signaling your neighbor. So in the case of having just a regular IP network and doing congestion isolation locally in the switch and not telling anybody about it, we still get a 25% gain. But once you tell your neighbor to isolate the same flow, that's where we really begin to eliminate head-of-line blocking. We're leveraging even another set of queues, if you will, buffering to allow the end-to-end flow control time to work. So you really avoid a lot of packet loss in that scenario too. We were getting a 54% gain in that scenario. And then the final one would be, we saw priority-based flow control has some negatives, some downsides. And so if we're still going to rely on it as a last gasp effort to never drop a packet, how can we reduce the amount of signaling priority-based flow control that would exist in the network? And we did the same mice and elephant separation, and we measured how fewer pause frames there were and how long the pause period was on for, and we got again 50% gains or 30% gains. So the feature itself appears to be effective. It seems to be a worthwhile situation, and we're trying to again build a network that will scale to larger size without having to tune and deal with all basically the complexities. And it does scale as well, so we get a pretty linear scaling. We looked at a small network of 128 servers all the way up to 1,000 servers, and the flow completion time didn't really grow, if you will, when we're using the congestion isolation feature. Whereas we start to see more problems with some of the others. So it appears to be a good scaling feature as well. All right, so what's next for us? We're in the process right now of developing the draft. There's a design team that has ad hoc phone calls to try to address some of those critical processes and make choices on how we're going to document that. And the question is, well, why am I talking about this here, and how can we participate? And this is really where we're doing this to try to support large operators, large data centers, hyperscale networks. And so is it something that's going to be useful for you? Is it a good approach? What are the requirements in your network? So getting that kind of feedback would be fantastic for us. And there's ways to participate. As Roger had mentioned, we have the NINDICA forum in the IEEE. And in the IETF, we've been holding side meetings as well, where we're talking about these kind of data center networks and what technologies we might need in order to scale it larger. So these would be great opportunities to participate in that as well. So at that point, I guess I could open it up to any particular questions you have, and also if there's any about any of the other talks as well, we'd be happy to try to address those as well. We can get the other guys up here if needed. So there's a whole bunch of useful references here that you can, again, more information about background technology and things that we're doing. So are there any questions? Yuri. Hooray.
Thanks, Paul. Definitely work of value, Uriel, too, with Intel. I have two questions. One is the definition of a flow in this context. Originally, it was all really port-based, and at layer 2, you don't really have a recognition of a flow. So that actually causes a blockage of other, call them transport level flows from the same source, and whether you guys are dealing with that problem. The other quick question, I have many, but I'm just going to restrict it to two, is incast normally involves potentially many flows, and that even if you put them aside, is still going to cause issues with the amount of buffering required.
Great question. So to the first question, what's a flow? So I'd say 802.1 has gone well beyond their boundaries these days of layer 2 and only looking at MAC addresses and things like that. So a flow is a full, 5-tuple here IP. And now you do have and we have specifications in IEEE 802.1 that define layer 3, layer 4 flows, if you will, now. So that's been something that we've done. So there is the question about, well, what do I do about overlay networks and like virtualization? And this is, again, we're expecting that we're not looking into the payload beyond the outer, the carrier, the passenger header. So a flow might be a full encapsulation as well. So you may actually have many subflows in there. There was a great question earlier about security, and obviously, if you have encrypted traffic on your virtualized network, we're not going to be looking inside that. So we're strictly looking at the outer flow, if you will, the outer headers. And so the second question that you asked, I forget, sorry, what was the second question was? Oh, incast, right. So you're absolutely correct too. Incast is clearly a problem. So we talk about incast in the paper, the Nindica paper, and we point out that really to solve the incast problem, we're probably talking about scheduled or some way of actually having the transport be more aware of this fact. So if you really want to solve the problem of incast, you have, like you said, hundreds, maybe thousands of flows all converging onto, really what we need is a different approach for a transport protocol. And there's been some research on that. There's NDP, I think was one paper at SIGCOM that was quite interesting, where you're effectively transitioning from the traditional TCP model of pushing data into the network and trying to probe for bandwidth that's available. You transition that to more of a pull mechanism, where the actual, before you can transmit, you have to have a grant, a request grant model. And so clearly, one has more latency, but it would avoid drops in an incast scenario. But the other pushing problem, doesn't really provide you the right visibility of what's going on in the network. So that the paper talks about a hybrid transport protocol that flips between pushing and pulling based on the state of congestion in the network. So yeah, so that's definitely an interesting topic, and again, we talk about that in the paper. That's probably more likely an IETF activity than an IEEE activity. But congestion isolation certainly intended to support large scale number of flows, not just one flow at a time. We're definitely gonna deal with the incast problem as well. All right. Any other questions?
Anand again. So how does the ASIC, do you think, will isolate the flow? I'm not able to understand that part. When you have multiple flows going through a port, that could be, I see you have different simulations, but I'm still not able to get my head around.
Okay. Yeah, so typically in ASICs they have we define 8 different traffic classes per port, which is, you know, priorities or queues, if you will. So what we're doing in congestion isolation is we're going to use 2 of them. We're going to take 2 of them. And so the way when we identify flow, when we were experiencing congestion in one of those, we're identifying flows that are causing that congestion by, you know, looking at the headers.
At the line rate.
Yeah, at line rate. So, you know, we're able to look in, and you may just sample, for example, a packet out of that queue that's backing up, and assume that the you know, that high probability that this flow is the one that's causing problems here. And so now you create an entry in a flow table that'll identify the packets from that flow as the subsequent packets. And now when they come in on the upstream port, we identify that flow. We're going to now queue them in the other traffic class as opposed to the original. So that's the isolation. We're taking that flow and we're isolating it into another queue traffic class. Now ASIC implementations may be more sophisticated than what we've defined in the standard. They may have more than 8 queues per port. Maybe they have hidden hierarchical queues and they have 16 or 32 queues or something. So there's even more opportunity in some ASIC architectures to isolate flows, more flows than the way we're working within the constraints of the 802 standard. So 8 queues per port.
And there are technologies like, I believe, DCQCN, where you do W-rate based signaling to the source, that are you, before you hit the buffer full scenario, you kind of notify the source that there is congestion that's going to happen and signal the source to slow down, right? So how do you think that's ineffective compared to this, or it's complementary?
Right. So things like, so DCQCN is defined to be the end-to-end congestion control for Rocky, for RDMA traffic. So that you have a source and you have a destination. When the destination receives packets that have been marked by the switch somewhere along the path that says there's congestion on this path, they send the message back to the source as a part of the acknowledgement. That's how DCQCN works. And so that's the end-to-end congestion control that causes the source to slow down. So we are in full support of that. In fact, we have to have that in place. We're expecting the sources to slow down. And meanwhile, while they're doing their control loop, we're isolating the flows to give it time so that we're not dropping packets. So fundamentally, we depend on either TCPs, you know, round trip ECN or DCQCN, something like this, that does the end-to-end congestion control. So we're relying on that. This is a big difference. There was congestion notification that was defined in IEEE that sent a source quench message all the way back to the source that told the source to slow down directly from the network itself. So that's not what we're doing. We're still in support of the end-to-end path. We're just amongst ourselves trying to identify the flows that are causing a problem and isolating them while the end-to-end loop can take effect.
Thank you.
Okay. Thanks.